All right, so I hope that you can see everything. And so I will report what we have been working on in Oxford last 2 years, I believe now. Mainly the results are obtained with Bernardo and Egor. And yeah, the motivation for this work is to obtain a kind of rule-based language, Datalog-like, which allows us to perform temporal reasoning. In particular, we would like to have reasoning which involve metric information, which has quite low complexity, or at least good algorithms that can be implemented afterwards, and it's also suitable for stream reasoning. And moreover, important thing that we are looking at is modeling time as dense, so over rationals, not, for example, over integers, like say in linear temporal logic. And what we did is we looked at this extension of Datalog with metric temporal operators, DatalogMTL. And in particular, we have constructed quite a big family of syntactical and semantical modifications of this. We have classified them according to computational complexity, constructed algorithms, and also looked about the possibility to use it for stream reasoning. So in our setting, we consider that you have some data sets, for example, from some sensors or something, which look like facts from Datalog. For example, that you have obtained a signal from pump number 24, and each of these facts is over some interval over rational timeline. For example, this one says that signal occurs continuously between 4.13 seconds up to 6.2 seconds. We can also have some facts over predicates which are binary or any arity, and also over points, not only over intervals. And then additionally, what you can also have, there is a program, so set of rules, which you can think of as ontology, which allows you to define new concepts or express some additional knowledge. It looks like Datalog, but the difference is that these atoms which you have in a rule, this A's and B, can also contain temporal operators, diamonds, boxes, since, and until. Just to give some intuition how they work, they're like in standard, let's say, metric temporal logic. But for example, this formula diamond minus, so diamond past, 1, 2, P, means that P holds somewhere in the past, because this is this diamond minus, but not anywhere in the past, but somewhere between -1 up to -2 seconds, let's say, with respect to the current time point. So this P needs to hold somewhere there. Box minus says that P needs to hold continuously in this interval, and Q since P means that P occurs somewhere in the interval I told you, and Q holds since P continuously up to the current time point. And of course, we've got also future counterparts of such operators, and moreover, this interval, which I use there, 1, 2, can be arbitrary over rationals. It can also have infinity. If you can have something like from 3.4 to infinity, something holds. And so this language is quite expressive. What you can, for example, express is that a node receiving reading for a signal with sufficiently high frequency flags the signal by sending a message to all neighboring nodes in the network, which will then also monitor the signal for a fixed period of time. And I will not go through these formulas, but notice that we can express something like high frequency. We can also have recursion, both non-temporal and temporal. So in time, you can also recursively pass information both to the future and to the past. And so we have considered computational complexity of reasoning in this DatalogMTL, this full language, and also in its fragments. So we have considered a number of fragments, linear, core, with only boxes, with only diamonds, and also we have considered both data complexity, so complexity with respect to your data set, and combined with respect to data and program. And moreover, we have considered this standard, let's say, Datalog language, first order, and also its restriction to only propositional case. So we don't have predicates, but only propositions. And we have this nice table of complexity results. So we know that the full language is P space in data complexity, X space in combined complexity. There are some other results there. What's interesting is that we have two fragments for which we know that at least data complexity is tractable below polynomial time, n-log space and TC0. So we have some good fragments in a sense. This is of a rational timeline. So we also considered lately what happens if rather than rational points, you have only integers, because then situation changes quite drastically. And so we have considered data complexity of such languages. So I will leave the left part of the table now, and the right part, which is about combined complexity, I will replace with the table for integer semantics. So this is what happens. And probably the most important information which you can get from this table is that if you go to integer timeline, and moreover, you assume that your language is propositional, so we don't have predicates, only propositions, then even the full language becomes tractable polynomial time in data complexity. Actually, it's NC1, so it's even below logarithmic space. So it's easy in data complexity to reason with this kind of language. And actually, those are kind of a new results that we'll present during KR. So we will discuss probably more details there. Next thing that we have considered is how to extend the language. So what we can add, and at first we started with negation. So it occurs that if you add classical negation in combined complexity, you become undecidable. So we have also considered kind of non-monotonic negations, semi-positive, stratified, which are well known in Datalog. And for them, we've shown that they do not change computational complexity. So you can have stratified negation, let's say, for free in sense of complexity. The data and combined complexity of the language do not change. So this is also kind of a fresh result, not published yet. And then we obtain some insights on the interplay between these operators, between complexity, what we can express, and we can use this to construct algorithms, in particular for stream reasoning. In stream reasoning, the situation is a bit different, right? You don't have data set as an input, but you've got a stream of facts which is potentially infinite. You don't know what will happen in future, what you will obtain. Program is the same as we had, but now the output is also a little bit different. We want to stream out also facts over some answer predicates, which we are interested in. So you want to stream out all facts which follow from data and program. One of the problems with this is that our language allows you to propagate information to both future and past. So you can have a rule saying that if P holds somewhere, then Q holds everywhere in the past. This is not really good in a sense that if you want to know if Q holds in time point 0, you can wait if it holds somewhere in the future and then so that you can derive it in 0, but you don't know how long you need to wait. You can wait infinitely long, right? So we have restricted attention only to fragment, which only propagates information to future, which is probably kind of suitable for some applications. Especially this example I showed you also is forward propagating only. And we have constructed algorithms for stream reasoning, sliding window algorithms, which are sound and complete. The problem is that these algorithms do not have bounded memory in general. So we have introduced 3 different ways to bound memory for these algorithms. And one of them is to disallow operators which are punctual. So they have these intervals which start and end in the same time point exactly. And so if you disallow this kind of operators, intuitively your program do not recognize 2 facts if they occur very, very close to each other. So if the gap is small, then this gap is not seen by a program. And because of this, we can use some tricks. It takes us the whole AAAI paper to prove it, but we can have some tricks to bound memory. Another way is to restrict your rules so that you only have linear derivations. If every derivation is linear, it means that it comes from a single fact in your stream. So if you obtain a fact in the input stream, then you know everything what is derivable from it, you can forget it. And the third thing is to adopt integer semantics. So notice that if we have our sliding window algorithm, then in a single window, there are infinitely many rationals, right? So potentially infinitely many facts you can store within a window. If those are integers, then of course you've got trivially bounded number of facts, which allows us also to show that.
1 minute, one to conclude.
Conclusions.
Okay, good.
Thank you. So yeah, so indeed, so we have considered these extensions of Datalog with metric temporal operators, which we believe it's powerful and useful language, and we know its complexity, its fragments. We know that it's suitable for stream reasoning. And what's the future work at the moment is to find algorithms which are implementable, and actually to implement them to find out how they work in practice. And also in the meantime, we are looking at other, let's say, theoretical questions. For example, what happens if we consider various different semantics of negation, like, for example, stable model semantics? What happens with complexity and algorithms? Okay, thank you very much. I think that this is the end.